Welcome everybody to our presentation of the keynote paper in the topic of Springback with the title Springback and Compensation in Sheet Metal Forming, Reconsidered as an ill-posed problem. So here you directly see that our focus in the presentation is also to give an alternative view on the description of the problem of Springback within a mathematical framework. I also want to say thank you to the co-authors. It's Dr. Hartmann, postdoc at our institute, and Maier, PhD student at UTG. When we have a look at Springback, we know Springback is a big issue. Most dimensional problems caused in sheet metal forming are more or less mainly depending on the Springback behavior. And there we have the stress distribution as the causing effect in sheet metal form. We know we have contact forces, elastic plastic behavior, and after releasing the contact forces, we have the deformation of Springback. So we have many influencing factors. It's definitely the elastic behavior of the sheet metal, especially also for the unloading, and then the sheet thickness, lubrication, tool geometry, and many more. Compensation nowadays is an accepted strategy to overcome these dimensional problems, and it's typically done in an engineering iterative process and at the ending in tool modifications. Okay, now when we see the classical approach, we can say the question we have to answer is how to design a tool and process to achieve minimum deviations between the target and the component geometry after Springback with respect to given process restrictions. So this task is written down, and typically we have 3 basic steps until we can come to these modifications. So first of all, we need the stress state. Stress state after the forming process when we have closed tools. So this is, let's say, not a big thing in most simulation tools within a given accuracy. Then the next step, also well established in our simulation packages, is calculate the Springback when releasing the stress for closed tools. So here we see a quite difficult example of a typical industrial part where we see typical deviations up to 7 millimeters in the corner areas. The Springback is in the direction where we don't want to go within our tools. Of course, our tool must go in the opposite direction, and then therefore we need measurement and a compensation strategy. So these 3 steps are here, let's see, from a view of engineering, which is done every day. And now we want to come back to the focus of our presentation to set this in a mathematical framework. So here we transfer this strategy, what we have shown in the last slide, into a mathematical description, where we see here the desired tool and die geometry. Then we have the measured geometry G, depending on the tool geometry and process parameters, and we have the CAD geometry or target geometry. So here we can measure a deviation between the desired and the current geometry, and in addition to that, we can also, like in nonlinear optimization, often use restrictions. These restrictions and can be in inequality or equality constraints, and a typical inequality constraint is undercut. Our tools must prevent undercut, so because then it would be impossible to form it. So undercut would be part of these inequality constraints, and also sometimes we have limitations within our tool realization, like the punch opening line, which is given, or that it's not allowed to change the blank holder geometry. So these can also be defined as equality constraint. So this is our mathematical representation of this classical engineering approach. Here we only have one forming operation. When we have a look in industrial applications, we not only have one stage. So as you can see here, we have for most automotive applications multi-stage processes. So where we have the first forming operation, we have cutting, restrike, calibration, and so on. So here we also have an important forming content in the first one, but also in the other stages where we can have forming parts and therefore also Springback. And now the question, how to formulate these real processes, multi-stage, in also the same mathematical framework as presented one slide before. When we go on here, we say, okay, we can enhance our formulation, and then the question, what's our customers asking for? So our customers are asking a final part within the given tolerance. That means here, when n is a maximum number, so we can say we have to minimize the deviation in the last forming stage. But we don't know how to do it, because also the other forming operation are influencing the final result. So here it's just the mathematical representation. Okay, final part must be within the tolerance, and we can have inequality and quality constraints for every stage. Okay, so here it's written down easily, but how to overcome this problem? So we want to highlight this with our example. That means even when we start here, this is our target function, and here we have the influencing geometries of all the intermediate stages. When I had my industrial time before academics, we also had many discussions how to do this. And at this time I said, yeah, what would be when the case when we demand that the deviations in every stage should be minimized. So then we have not the full degrees of freedom. So we have additional constraints based on experience that we say, okay, when the deviations are not too big, we have the option to minimize them within a suitable time. So this can also be written down in a mathematical framework that we say minimize the deviation in all individual stages. So we have here the sum of all the deviations, and they are not independent from each other. That means we have to start with the first one, and the second one is depending on the first, and they'll go ahead within our different stages. That means we minimize the first one, the result of that is the incoming geometry of the second one, minimize this, then minimize the third, the fourth, and finally the fifth one. So this is also a suitable strategy, but it's implicitly part of when we just minimize the final one, but we have the demand of more constraints within the prior geometries. That means at the end, typically with this strategy, we are maximum as good as when we just do it in the last one, but because we are losing some degrees of freedom, in general we will be not so good like when not having these constraints. So, but we will see it also later in the short example. Okay, now we can say, let's go on. we have a description, we can go for a solution because now a mathematical equation. Then we can have a look in math books, find strategies, how to solve it. But then normally the prerequisite of a well-posed problem occur. So that means, okay, perhaps it can work, or perhaps it cannot work. Therefore, we should consider first the structure and the basic limits of our formulation. What's part of the so-called well-posed problem? When we have a well-posed problem, we go back to Hartmann's work. We should, or we must, ensure a priori that the solution exists. Also, the solution must be unique and it must be robust. That means here in the mathematical description, the behavior of the solution changes continuously with the initial boundary values. In engineering words, small changes in the incoming variables should also lead to small changes in the output result and not a chaotic behavior. If one of these 3 points is not fulfilled, then we have an ill-posed problem. Of course, also when more of them are not fulfilled. So when we have a look for Springback, in general, the solution to exist, we hope, in most cases it is, but not always. For example, with the undercut, what we have mentioned just before, it can happen, and then we don't have the tool geometry to come to a solution. Also, especially for the multi-stage problem, there can be different ways for the same geometry. So the solution of tool geometry where we're looking for is not unique. And finally, also the robustness is not always fulfilled. So from this point of view, our problem is in many cases ill-posed. And so it's not a wonder that sometimes established solution strategy, which comes to a result for one example, fails for another one. Okay, so let's say transfer this problem to sports. When we are a manager of a football team and we know we have an ill player, what we can do? First, we can send him on the field. Hope that the illness is not too bad and we will have success also with the ill player. But on the other hand, we have the option to give him in medicine, that he will recover and then he will have full strength afterwards. So same idea can be done also in the mathematical framework of ill-posed problems. And there we can go back to Tichonov's framework that regularization is a really powerful medicine for problems which are ill-posed. So what we do from the basic idea, here we have our classical problem and we add, based on experience, based on the type of problem, an additional term where we can increase robustness and transfer this ill-posed problem to a well-posed problem. So it's a little bit like voodoo, you could say, but yes, it is, let's say, based on experience, but if you put in enough experience, you see that with the mathematical knowledge and the, let's say, experience, you can come to really good results. So this alpha, also called in literature a hyperparameter, based on the structure of the problem and experience, can help us to change the mathematical description and to come at the end to a robust solution because we have transferred our ill-posed problem to a well-posed problem. So when you write it down, please don't be confused. Here we have our classical data term, what we introduced some slides before, and we have our regularization term. And in the regularization term is depending on our die geometry and the process parameters, And we have added here the, let's say, the joker vector phi, where we can put in also experience, how to use it, how to set the hyperparameters, because this is really helping us to come to better solutions. Okay, so we have a small modification of our problem, and when we have a small look on the type, we can also find our basic components of the classical engineering strategy in this description. So here we see the geometry, where we have the stress state and the Springback, unelastic behavior, unelastic modulus, and so on. Also, we have the norm, where we see that we have a difference between the target geometry and the real geometry. So here's the measurement topic part of this description. And finally, with the regularization term and the minimization, we have the compensation. So all three elements you will find back in this mathematical description. So now we can go on. So let's come a little bit to industrial applications. So first, the determination of the stress state. We all know it's even state of the art, but we should do it in an accurate way, because if you have a wrong prediction of the stress state, of course you will have a wrong Springback prediction. So here the die geometry, process parameters, variables, material parameters, material cards, and so on are really important and should be done carefully. Then, sometimes underestimated is the Springback prediction. Why it's sometimes underestimated? Because we know that also the elastic behavior of unloading is sometimes changing, or in many cases changing, with the rate of deformation. That means our elastic modulus is significantly lower than our initial loading modulus. And we have many works, and in real examples for real materials, we have a decrease of 10% of the unloading modulus in comparison to the loading one. And if you sum it up, you see that it's really an important thing to take care of it. Also, what I want to mention, for a typical forming operation, the stress state in plasticity, which elastic plasticity, in the end is so-called incompatible. That means, due to the plasticity, even after the unloading, we have a remaining residual stress state in our component. So, due to these incompatible modes of plasticity, not the full set of stress after forming is causing Springback, and we have this, especially for bending operations and so on, a significant amount of residual stresses in our final part. So here you see also a typical way of Springback, but it's not main focus of the presentation today. Then, also absolutely not trivial is the measurement. In a simulation, it's quite easy, because we always have the same coordinates and we know the material points before and after. When we compare real form parts with the CAD geometry, it's much more difficult, because there it's not obvious in the first step which material point is that one which had a contact to the tool when you just measure the part after Springback. So here also circular methods should be applied, and also strategies. So here also we will see a presentation of Maier, where we have the material point tracking method as a suitable one to overcome this problem. And now the final topic within the framework, which is making us problems, is the robustness of the solution. We heard we have in many cases an ill-posed problem, and there also the effect of stochastic deviations occur. So that means our difference between target geometry and real geometry is having a stochastic part and a so-called deterministic part. So this stochastic part can be caused by deviations of the material, changes in lubrication amount, and so on. From the mathematical point, it's a high frequency deviation, and the deterministic one, it's a low frequency deviation. Here also we added this vector phi, because it's, if you just have formed one part, you need some experience how to differentiate between the amount of stochastic and deterministic deviations. So also a big topic, because typically for the compensation we only want to compensate the deterministic part, because we want to have an accurate part for all allowed deviations within our process. And when we have only small data, when we have only the first few produced parts, this is really a hard topic, and we need also strategies to overcome this, what we will present soon. Okay, so the updating rule for nonlinear optimization, in the classical way we have just our data term, and in the alternative way we have the regularization. So here some published procedures, strategies exist, which I want to discuss just briefly. So the most applied and in many commercial packages available procedure is the so-called displacement adjustment method. What we do? We calculate the difference between target geometry and our first produced part, and then we update the geometry by just the negative value of the deviations. Due to the ill-post type, also here some experiences should be used, and this beta is just an experience way that you should not give the full displacement in the other direction, but the amount of it, typically 80%, 70%, sometimes 50%. So this is based on the experience, and if you do this, you see here for our given part that after 2 iterations we will see that we can come to a suitable amount of geometry, but also here we see a problem with occurring undercut, that this area can't be optimized, and we have to change the geometry, or we have to live with the deviations. Here, with the displacement adjustment method, we have only a displacement vector, and with the displacement vector we have the option for, especially for tension and compression, to come to a good result. We have bigger problems when we have also stretching and bending effects, because bending typically occurring a springback in rotation and stretching in displacement. And if you just invert the displacements, you can cause bending stresses which lead to problems in oscillation in your solution. So in the beginning of the 2000s, there was an idea of the so-called spring forward method. What the idea is just, okay, in the stress state we have 6 degrees of freedom, in the displacement only 3. When we have 3 displacement plus 3 rotation, it should be okay when just inverting the stresses. So we calculate the stresses, invert the stresses, and do a spring forward in the direction of the tool modifications. So for simple geometry this works well, but for complex geometry we often fail. Why? The reason are the residual stresses. Because the incompatible deformation in plasticity, we only have amount of stress causing the springback, as I mentioned before. So this is the reason why I do not recommend the full published spring forward method, but instead of this, a combination of the displacement adjustment and the spring forward idea. So there are some works where we can find a let's say, a compatible stress state just based on elasticity, because elastic deformation are always compatible, and then we can make a so-called displacement compatible spring forward approach, where we also have the chance to overcome the problem with the residual stresses. So these strategies are still based on the, in many cases, ill-posed problem definition. What we want to highlight, the options of the regularization and the well-posed transfer after having the regularization term. So here we have a two-stage forming process of a simple geometry, where we see here the first drawing step, for material DP800, thickness 1 millimeter, and a second forming operation. The compensation here is done by the control point displacement adjustment method, and also we assume that the flange areas are considered as waste and are not added in our target geometry, where we want to have a suitable accuracy after Springback. So when we just apply the displacement adjustment method and the deviation in the last stage, we see here a quite good result. What we also see that we still have some deviations, especially in the radii, but due to the choice of these two norms, we want to minimize the resulting vector of all elements. Also, now when we minimize the deviation in the first and the second stage, we see, okay, also here a result occurs, but as expected, it is not as good as the one when we just have the degree of freedom for all forming operations. So here also say, yes, it's quite fast, but at the end, the deviations are higher when we have the minimizing in both operations, instead of saying our target function is only based on the second stage. Okay, now we assume modifications with our incoming material. Let's say check the robustness when we say our material can change. In most critical ones, it should be plastic parameters. For simplicity, we have chosen here the elastic parameters. So we have modified the Young's modulus, and we see we can also calculate the deviations afterwards, where we see that here we have an increase of the deviations, and also when we have minus 10%. So I go back that you see also in this histogram the amount of elements within it here, standard plus and minus 10%. Also in individual stages we see that we have big deviations, so we focus in the following only of the left side, where we minimize the deviations only in the second forming step. Then we can reformulate our basic mathematical approach, and also what is, let's say, a possible way of using it, that we can differentiate in the robust and based on stochastic deviations, and also sometimes it can be helpful to add one within control. So for this controllability part of the regularization technique, it is really a big chance, because now we have a mathematical formulation where we can directly integrate sensor information within the optimization option. So this is also a new part of our own paper, but we want to highlight here that we have the chance within this given description. Okay, so now we want to see how we can come to a solution in this simple example with this variation of the Young's modulus, which we can say it's a stochastic deviation. So here we have the conventional approach where we just add the beta, and on the other hand we can say we have the regularization term based on the stochastic deviation and also use the displacement adjustment method, but we have the deterministic part calculated in that way. So we want to do in this step, based on the information how material parameters can vary, a compensation of a best fit which is applicable for all of the possible deviations, plus 10% and minus 10%. And here you see the results. Okay, here we have our modulus, what we optimize with the displacement adjustment method, and then we have variations, and when you see the histogram, we see that also in bigger areas we have deviations. And then here with the enhanced method, where we optimize in one step all possible options, we see on the one hand that we are, if you see the histogram here and here, that we are not as good for the most likely option, but we are definitely much better also on the boundaries. And therefore we have a compensation with a higher robustness. So here we see that without big effort, just with the reformulation of the problem, we were able to take care of these stochastic deviations and to have a more robust optimization of our tool geometry. And this is what we recommend to do, also to reconsider as a big take-home message of the presentation, that even with a little bit mathematical effort, we are nowadays able also to take care of these stochastic deviations and to have a higher robustness in Springback compensation. So let's come to conclusions. What really I want to give you as a key aspect of the presentation, please be aware that Springback compensation in many cases is an ill-posed problem. And don't be too surprised when you see that conventional solution strategies occur to oscillations or not come to a result. The framework, what we opened here, is also that we have the possibility to take care of multi-stage formulation of the problem, that we are able to change the objective functions, and also how we can include robustness and options of controllability within the whole framework to be possible to take care also for industrial applications. And what at the end we have compensation methods where we have updating rules, and we are able to put in sensors, but also a big field of research where you're always welcome to discuss it with us, how to do it, how to have the best position of sensors, how to take care of controllability and robustness and so on. So with that, I want to say thank you. Also thank you to our sponsors. In this work we have sponsors of the EFB and the DFG, and you're welcome for questions. Thank you very much for your kind attention.